Waka waka! Voltage, current, power, and resistance. Let's see how much stuff I can cram into one individual lesson, which is 9.3. Alright, so let's start off with current. Current is going to be the amount of something. In our case, we're going to deal with electrons passing a certain point over a certain time. So coulombs, that's our charge, over seconds, which is an ampere, or simply just amps. The more particles we have flowing, the larger the current. The less particles, smaller the current. Next thing we have is voltage. Voltage is what's going to push these electrons or charge through the wire, which causes our current. And this is caused by electric potential, like we went over in 9.2. This is measured in volts and is directly proportional to the current. So one goes up, the other one goes up. One goes down, the other one goes down. Yay! Look at animation, they swirl. Next thing is resistance. Resistance is the measure of how hard it is to move these particles through the material. More resistance, the harder it is for the current to flow. And its symbol there is an omega, which means ohms, resistance. So there's three basic things that you're going to need in order to make current flow. You need a conductor, you need something to push the material through the conductor, and then you need some sort of resistance. Ideally, we use wire, a battery or power source, and then the resistance is whatever going to draw away from that. A light bulb, radio, speaker, fan, noisy bell, I don't know, whatever you're using to power. Here's a diagram of a simple circuit. What we have is the wire right here. This is our light bulb over here, and then this is our power. I shouldn't use power. I'll just use potential. Right? And as you might notice, the negative is flowing towards the positive end. Right? That's where this potential is coming from, negative to positive. The wire has the electrons in it. This allows the battery to give a potential difference, which causes the negative to be attracted to the positive and then allow electricity to flow. So in order for this to work, our conductor is a wire. The voltage in this case is our potential difference. It goes from negative to positive, and then our resistance is our light bulb. How fun is that? We can draw this circuit using a schematic, and the way a schematic works is we have lines that represent wire, a nice little squiggly line which represents our resistor. Sometimes it represents a light bulb, sometimes it represents a fan, sometimes it represents whatever you're going to put on there. And then we have our battery or power source. Right? And then the flow of electricity is always going from negative back to positive. So positive, negative. Here are some other symbols that we could look at. Use lamps, voltmeter, that's what's going to measure our volts, and then ammeter, that's going to measure our amps or our currents. Some more examples of schematics. We have a drawing of a circuit, so this is just a drawing. We have some light bulbs, some batteries. That's what the schematic would look like. Here we have another drawing of a circuit, and this is what the schematic would look like using those symbols. Notice with this one, the current, as it flows from negative back to positive, only has one way to go, right? Only one path. Anything happens to this path, a break or open, current can't flow. Over here, though, the current, as it goes through, could go this way, or it could go this way, or it could go this way, and then it comes back. So there's multiple pathways. So that's a more complex circuit. We'll talk about those later. Formula-wise, we're looking at Ohm's law, where our current is equal to our voltage divided by our resistance. And then we have this little silly picture that kind of depicts what's happening. Alright, practice problems. First one, I want you to find the currents. So, Ohm's law, I equals V divided by R, 9 divided by 10. Our current is 0.9 amps. Alright, again using Ohm's law, I equals V R. We could figure out the total voltage, or the total resistance here. So, current equals 2, voltage equals 10, so our resistance equals right? Well, 10 divided by 2. So our total resistance equals 5 ohms. But I want to know just this one right here. So these two would equal 5. So 5 equals resistor 1 plus resistor 2. So resistor 2 is 3 ohms. Whoa. Trippy, Mr. H. Alright, power. Power, very similar to energy. It's the rate at which this energy changes, so it's measured in watts. Power is equivalent to current times voltage, or even current squared times resistance. And I put in this nice chart so that we could go through and you could see that there's multiple ways to find any of these. It can be very helpful, especially on homework. Alright, so let's do some practice real fast. There's a couple of ways that you can go about doing this. You can use I times V, you can use R times I squared, or V squared divided by R. I'm going to go ahead and do V squared divided by R just because it's going to be a little bit easier. So V squared divided by R is going to equal power. So 10 squared over 20 plus 19 plus 20, 59, and you should end up with 1.69 amps. Again, you don't have to do it that way. You could also figure out your current. Different color. Right? 10 divided by 59, and then take that and do I squared times your resistance, or I times V right? Either three ways are going to give you power in watts, not amps, watts. Oopsie, doopsie, poopsie. Alright, so that's about it. I will see you next time, hopefully. If not, don't tell me about it. Ignorance is bliss. Alright, goodbye.